you propose a proper mathematical definition of these things which you do actually see under a microscope. So there's some irregularity, but it's not an obvious mathematical singularity. So I've roughly said this already. So what is a defect? For me, it's either a region of sharp gradient or localized energy concentration. I have here some pictures. Now, as you might expect, defects, they can be modeled on different scales mathematically. Now, the first approach is a continuum PDE based approach, which is also my approach. This is very popular in the mathematical community, but it's also the least detailed in some sense. It's the least detailed because these continuum approaches, they contain no information about either the molecular shape or the nature of the intermolecular interaction potentials. But they're typically very successful in at least giving us a coarse averaged picture, and they're also computationally inexpensive. A second approach, which is very popular in the computational chemistry discipline, is to simulate very detailed intermolecular interaction potentials, which contain potentially very detailed information about the molecular shape or the nature of the intermolecular interactions. But the drawback is that even though these potentials might be very accurate, they're computationally very expensive. So it's not really viable to try and use these potentials to simulate defects in a macro-scale system. So a third approach is what we call possibly a multi-scale approach, where you might try and couple two different models together. So you might want to use a continuum model everywhere away from a defect core and try and couple it to a detailed microscopic model near the defect core. But this is a fairly new approach, and this is very much work in progress. So coming back to the main body of this talk, so I'm really just going to be focusing on continuum PDE based approaches to defects in this talk. And the question of interest for me is, what is the best that these coarse averaged theories can do? Now I'm going to start with the simplest continuum theory for nematic liquid crystals, which is the Osane-Frank theory for nematic liquid crystals. So you've already heard a bit about that from Professor John Ball, but just to make the talk self-contained. The Osane-Frank theory is the simplest continuum theory for nematic liquid crystals because it is restricted to strictly uniaxial nematic materials with a constant degree of orientational ordering. And just to remind you, uniaxial means a single preferred direction of molecular alignment. And the Osane-Frank theory can only model this direction, this one direction. It can't even account for any variations in the degree of ordering about this direction. It can only describe this direction. As you might expect from what I've just said, the main Osane-Frank macroscopic variable is a unit vector field n. So this n, as you might expect, again, it takes its values on the unit sphere, because the unit sphere is the space of all admissible directions in 3D. So and the physical interpretation is that this n, it represents the single preferred direction of molecular alignment. So you have one macroscopic variable, and it represents the single preferred direction of molecular alignment of a uniaxial nematic. Now the Osane-Frank theory is a variational theory. So it assigns an elastic energy or an energy of distortion to every such unit vector field n. And the stable equilibria, which is the ones that you would expect to observe in practice, they are just minimizers of this Osane-Frank energy functional subject to the imposed boundary condition. So it's a nice variational framework. Now the Osane-Frank theory, yes?
Your model is not Osane-Frank model. You're very simple.
It's the one, but I mean, if you have three constants, it would be, it's the one constant approximation. Well, it's a special case of the Osane-Frank if you set all the elastic constants to be equal. But what I'm roughly saying isn't so much dependent on the values of the elastic constants, because so my work is really modeling defects in the Landau dish, and this is sort of starting with the simplest.
Osane-Frank model of Landau equation, even not a elliptic system, so the complete.
Well, it is elliptic for some values of the. I mean, if you have the three constant, I mean, there's a.
If three constant equal is Laplace. If not equal, you're not a elliptic system. So the nematic you cannot call Osane-Frank model.
I thought there was a paper by Hart, Kinder, and Lin where it is elliptic for some choices of the three. But at least in the one constant case, I think is just harmonic maps, and it's very, but in one case, one way or the other, the Oseen-Frank theory is nice in the sense that the defects have a very straightforward interpretation. They're just points where n is not defined. So they're just singularities in your unit vector field. And if you sort of restrict yourself to the harmonic map case or the one constant case, although I think there are results in the three constant case by Hartkinder and Lin, although I thought there was a paper, then defects are actually very well studied in this sort of model sort of system, this reduced case of the Oseen-Frank, if you like, because there are rigorous results on the number of defects. So there are bounds, upper and lower bounds on the number of defects. There are results on the structure of the defects. What sort of unit vector field profile would you expect near a defect? There are results on the locations of the defects. So if you restrict yourself to at least a reduced case of the Oseen-Frank, you have a good picture of the admissible defects. And I guess if you move to the three constant case, it's harder, but I thought there were at least results on the Hausdorff dimension of the defect set by Hartkinder and Lin, even when you have the full three constant case. But you still have a rigorous definition that you're looking for singularities in a unit vector field. So at least you have some way to interpret these defects. But then the problem with the Oseen-Frank theory, which is that it's ultimately a very simple theory. It can't even account for biaxiality. If you restrict yourself to the one constant case, which is probably the only analytically tractable case, then you're left with only point defects. You can't even describe line defects or higher dimensional defects. So you need a more sophisticated theory if you really want to describe the sort of structures you see in liquid crystalline systems. So this brings me on to the Landau-Dijen theory. Now the Landau-Dijen theory is a more powerful theory than the Oseen-Frank theory. It's again a continuum theory, and it's more powerful because firstly it can account for uniaxiality and biaxiality, and secondly, as you will shortly see, it's not really restricted to point defects. It can account for defects of all dimensionality. So it's not just about point defects or line defects. In principle, it can account for defects of all dimensionality. The Landau-Dijen theory, like I've already said, is again a macroscopic theory. So it describes the state of a nematic liquid crystal by a macroscopic order parameter, which is the Q-tensor order parameter, which in principle can be defined in terms of anisotropic macroscopic quantities like the dielectric anisotropy or the magnetic susceptibility. But loosely speaking, the Q-tensor order parameter is just some sort of a macroscopic measure of the anisotropy present in the system. And from a mathematician's point of view, the Q-tensor order parameter is just a symmetric, traceless 3x3 matrix. Because it's symmetric and traceless and 3x3, there are 5 degrees of freedom. And these 5 degrees of freedom, they can be related to the degree of orientational ordering and the directions of preferred alignment. Now, since this talk is really about the uniaxial or biaxial nature of defect cause, I'm going to make this uniaxial and biaxial classification a bit more technical. Now, the Q-tensor order parameter, like I've already said, is a symmetric traceless 3x3 matrix. So from the spectral decomposition theorem, we can obviously write it down in terms of its eigenvalues and its eigenvectors, which is what I've done there at the top. And the sum of the eigenvalues is just 0 because it's a traceless matrix. Lambda 1, lambda 2, and lambda 3 are the eigenvalues. N, M, and P, they are the eigenvectors. And just to quickly take you through this, the Q-tensor order parameter is isotropic when it has 3 equal eigenvalues. It is traceless. So if you have 3 equal eigenvalues and it's traceless, all eigenvalues are just 0. So the Q-tensor itself is 0, which indicates complete loss of orientational ordering. Now the Q-tensor is said to be in the uniaxial phase when there are 2 equal non-zero eigenvalues. If there are 2 equal non-zero eigenvalues, then the Q-tensor order parameter can be written in that more compact form there on the slide. And here, the only things that need to be taken, sort of the points that I want to make here, is that N is the single distinguished direction of preferred molecular alignment. That's all you need to remember, in the sense that the directions perpendicular to N are physically equivalent, and the minus 3 lambda that you see there, you can interpret that as being a scalar order parameter that somehow measures the degree of orientational ordering about N. And the third case is the biaxial case, where there are 3 distinct eigenvalues. The biaxial case is mathematically pretty difficult anyway, but there's clearly a secondary direction of alignment. It's harder. Now, the Landau-Dijen theory, like the Ose-Frank theory, is also a variational theory. So there's an associated Landau-Dijen energy functional. Now, the Landau-Dijen energy density, as you might expect, is a nonlinear function of the Q tensor and its gradient, grad Q. And here I'm working with the simplest possible form of the Landau-Dijen energy density. So I'm really making things as simple as possible. Now, in the simplest case, the Landau-Dijen energy density has just two separate components. The first component is what I call the thermotropic potential. If you look at the formula for the thermotropic potential, I'm just taking it to be a quartic degree 4 polynomial in the eigenvalues of the Q tensor order parameter. This is the bare minimum that you need to even get a first order phase transition. So it's pretty minimal. It's just a quartic degree 4 polynomial. The A that you see here is just, you can think of it as being a temperature dependent parameter. And I will actually vary A in my analysis. So it is actually a parameter in the analysis. The B and the C, they're fixed material dependent constants. I'm not going to do anything with them. And the purpose of this thermotropic potential, if you like, is just to somehow dictate, at least in the spatially homogeneous cases, and this we've already heard before this morning, is somehow just to dictate the preferred phase of the liquid crystal material, whether it wants to be uniaxial, biaxial or isotropic according to the temperature. The second component is what we call the elastic energy density. Again, you can have far more complicated forms. Professor John Ball had 3 elastic constants, 4 elastic constants, but I'm again working with the simplest case, the one constant case if you like, where the elastic energy density is just grad Q squared, sum of the squares of the first derivatives of the Q tensor. And the purpose of the elastic energy density is just to penalize any spatial inhomogeneities in the system. And the L that you see here is a small material dependent elastic constant. And the energy minimizers, or the stable equilibria, they would be either global or local minimizers of this energy functional, subject to the imposed boundary conditions. And the trick is that they somehow have to balance both of these components. So these energy minimizers, which is what we're interested in, because we somehow want to mathematically characterize defect patterns in global or local energy minimizers, they are solutions of the associated Euler-Lagrange equations. Now, what the Euler-Lagrange equations, if you looked at the energy functional on the previous slide, they're just a nonlinear elliptic system of 5 elliptic coupled PDEs. So these energy minimizers are actually classical solutions of these Euler-Lagrange equations. They're actually, you can use results from elliptic regularity. So, and this is already published in one of our joint papers. You can prove that these energy minimizers have to be analytic. In fact, any solution of this system of PDEs with possibly some energy growth condition, it has to be analytic. And then the question of interest then is, if we just restrict ourselves to energy minimizers for the time being, then these energy minimizers are analytic. And then the question is, if they are analytic, then there is no obvious mathematical signature of a singularity. And how do we mathematically interpret defects in a Landau-Dijen framework? Well, this is a pretty non-trivial question, and I don't think there is a general consensus as yet. But we do have two possibilities, two possible mathematical definitions, if you like. The first one was brought up by Professor John Ball in his talk today, and this was probably mentioned in the first paper there, the 2010 paper, is that the energy minimizers are analytic. Now, there is a theorem that the eigenvectors of this minimizing Q tensor, they will have the same degree of regularity as the Q tensor itself, as long as the number of distinct eigenvalues do not change. So if the eigenvector, if you want to think of these defects as being singularities in the eigenvectors, then these singularities have to be localized on interfaces where the number of distinct eigenvalues changes. So if there are any singularities in the eigenvectors, they have to be localized on either isotropic uniaxial interfaces, isotropic biaxial interfaces, or uniaxial biaxial interfaces. And I think this was briefly mentioned in the 2010 paper. Now, in a subsequent paper, I tried to look at the definition of defects in terms of some sort of energy concentration, because I do tend to think of defects as being localized regions of energy concentration. So we kind of looked at the renormalized energy. So the renormalized energy, we were looking at the Landau-Dijon energy inside balls of a certain characteristic radius r. Now this radius r is proportional to the nematic correlation length. So we were looking at the energy inside balls of radius comparable to the nematic correlation length. Now the renormalized energy is the total energy divided by the radius of the ball. And what we found was that if the ball contains a defect, maybe a singularity of the eigenvector, say, then this ratio will tend to a non-zero constant in the limit of vanishing nematic correlation length, or you can think of this, or in the limit of vanishing elastic constant, or in the limit of vanishing radius. You can think of it in a number of different ways. But if it does contain a defect, the total energy has to vanish because the solutions are analytic. But if you look at this renormalized energy, it will tend to a non-zero constant. But on the other hand, if the ball does not contain a defect, then this ratio will tend to zero. This is obviously not a complete description, but it was reasonably effective, at least in the uniaxial case, in terms of trying to define defects in terms of renormalized energy concentration. And this was proposed in the second paper here. So this pretty much brings me now to the main theme of this talk. So my real question, I mean the crux of this talk is that we have these energy minimizing Q tensors. They're analytic solutions of this elliptic system of PDEs, and the aim is to somehow mathematically identify and locate these defects and try and say something about their structure. And in the work that I've done so far, it comes across that in this sort of analysis there is a crucial distinction between uniaxiality and biaxiality. And that is because if we restrict ourselves to uniaxiality, then if you look at the formula there, a uniaxial Q tensor just has 3 degrees of freedom, because there are 2 degrees of freedom associated with your n, which is your single distinguished direction of molecular alignment, if you like, and then there's your scalar order parameter. So you have just 3 degrees of freedom. So in particular, if you have a 3D domain, then you're effectively studying maps from a 3D domain into a 3D target space. And for people who do Ginzburg-Landau type of theories, this makes the mathematics, at least, it makes it a fair bit easier if you're just studying maps from 3D into a 3D target space. But on the other hand, if you sort of deal with fully biaxial Q tensors, you have 5 degrees of freedom. And we couldn't fully resolve is how do these extra degrees of freedom, how do they actually manifest what can we say, how do these extra degrees of freedom manifest themselves in physical phenomena? What's the sort of physical signature? So we didn't make too much progress in the biaxial case, but we do have things to say in the uniaxial case at least. So for the rest of the talk, I'm just going to focus on a very nice model problem. It's again very simple. I'm just going to look at a spherical droplet, and a 3-dimensional 3D nematic spherical droplet filled with liquid crystal material. It has radial boundary conditions, so this just means that the boundary is treated so that the molecules in contact with the boundary have to be pointing radially outwards. It's very intuitive, homeotropic boundary conditions, and we are working with low temperatures. So we are working with temperatures where your thermotropic potential, it likes to be in an ordered nematic phase as opposed to the disordered isotropic phase. And the question that we're trying to address here is what can we say about defect structures in this very simple problem of a spherical droplet with radial boundary conditions for low temperatures. Now this problem, it's been very well studied in the literature, at least from especially numerically and also to some extent theoretically. There is also some analysis, also although our results are different to what is there in the literature, but it is a well studied model problem, at least numerically, and is generally believed that there are 2 competing equilibrium structures. So none of this is a proof, these are not proofs, but it's generally believed that there are 2 competing equilibrium structures. The first structure is referred to as being the radial hedgehog solution in the literature. Now the radial hedgehog solution, if you like, as you can see from the picture, is a perfectly radially symmetric structure. It is really the most symmetric solution or the most symmetric structure consistent with this boundary value problem, with the molecules oriented identically radially outwards everywhere away from the droplet center, and you have a single isolated isotropic point at the droplet center. So here I have some pictures of the eigenvalue profiles. They're not mine. I think they're taken from one of Chuck Gartland's papers. But if you look at, so these are numerical, if you look at the eigenvalue profile, these are all three eigenvalues, but you can see that there are two distinct non-zero eigenvalues everywhere away from the droplet center, because the horizontal axis is the radial distance away from the center. You look at the picture and you see that there are two non-zero eigenvalues everywhere away from the center, so it's perfectly uniaxial everywhere away from the center, but at the center all three eigenvalues vanish. So you have a single isolated isotropic point at the center, and from what I've already said, you can interpret this isotropic point as being a defect point. Although nothing really funny happens in the solution, but you can think of this one isolated isotropic point as being a defect point, if you like. Now the second solution, some people call this the biaxial torus. I call it the disclination loop, but it's just a matter of terminology. But effectively, this is a different solution which has also been numerically found. And the key distinction here is, again, if you look at the eigenvalue profile, again this picture is not mine, but if you look at the numerical eigenvalue profile, you will see that far away from the droplet center, so again you have the radial distance from the origin on the horizontal axis, far away from the center you again have two distinct eigenvalues, which means that it's perfectly uniaxial sort of far away from the center. It's perfectly uniaxial at the center, but in the middle you have a band of three distinct eigenvalues. So you have a biaxial shell, an intermediate band, biaxial band around the droplet center. So informally, if you look at the picture on the left, informally this is saying that this solution, it preserves the radial symmetry of the previous radial Hedgehog solution away from the droplet center, but it breaks the radial symmetry near the center, and you can interpret this biaxial shell, if you like, again as being some sort of a defect structure. Now, so from what I've just said, so this is all pretty much still known territory. It's been published in the literature before. We have a spherical droplet with radial boundary conditions. We're working with low temperatures, and numerics suggest that there are two different competing equilibrium solutions. There's the radial Hedgehog solution, which is perfectly uniaxial and radially symmetric with an isolated isotropic point. You have a disclination loop solution, which has this biaxial shell around the center, but it has lesser symmetry. But what is counterintuitive is that it can be proven both theoretically and numerically easily, is that the disclination loop solution, which has the lesser symmetry, is energetically cheap, it's energetically inexpensive, it's energetically preferred to the more symmetric radial Hedgehog solution for low temperatures. But again, this is not a proof, but just to give you some heuristics, if you look at the formula for the Landau-Dijon energy functional, you will see that the energy density has two separate contributions. There's the thermotropic potential, and then there's the elastic energy density. Now what happens is that as we move to lower temperatures, the isotropic phase becomes more and more expensive. In particular, it's a maximum, it's a local maximum of the thermotropic potential. So very informally speaking, the disclination loop solution, it avoids this energetically expensive isotropic phase at the expense of breaking the radial symmetry near the center. So it has lesser symmetry, but it avoids the energetically expensive isotropic phase. So there's some sort of a delicate balance between symmetry and energetic considerations. And now we need to mathematically quantify these concepts. So just to remind you, we have this spherical droplet in 3 dimensions, we have the radial boundary conditions, and we have low temperatures. We have these two solutions, the radial Hedgehog solution, which is perfectly uniaxial and radially symmetric. We have the disclination loop solution with this biaxial shell. Now we have addressed, so this is a recent paper, 2 separate but closely related questions. The first question we asked ourselves was that, yes, the radial hedgehog solution is a uniaxial solution for this problem. You can actually analytically prove it. But the question is, are there any others? Are there any other uniaxial solutions that perhaps we simply have not found? So can we give a complete mathematical characterization of all uniaxial solutions for this model problem? Because the radial hedgehog is one example. And unless you can prove some uniqueness results, there may be others which you simply have not found. And the second question was, the previous discussion, we're only just looking at two separate solutions. You're looking at the radial hedgehog and the disclination loop. But the bigger question for us was, is biaxiality a generic feature for low temperatures? So it's not just a matter of looking at two different solutions, the competition between two separate solutions, but to answer a bigger question, or what I think is a bigger question, is biaxiality sort of inevitable for lower temperatures? Can we prove it? So here is a statement of our main result, and then I'll present the main ingredients of the proof. So the statement of our main result is we take this relatively simple form of the Landau-Dijon energy, we minimize it on this three-dimensional macroscopic nematic droplet subject to these radial boundary conditions. The radial boundary conditions are encoded into this QB that you see on the slide. I just want you to spend a few minutes looking at the formula for QB. If you look at QB, you will see that it is perfectly uniaxial. You will see that it is perfectly radial because the leading eigenvector is x over mod x, which is just the radial unit vector. You will also see that it has constant order parameter s plus. You don't need to worry too much about where s plus is coming from, but this choice of s plus guarantees that this QB is actually a minimizer of the thermotropic potential. This is roughly saying that the boundary is in some sort of thermal equilibrium. We are working with low temperatures. So in all our mathematical analysis, A, the first parameter, is less than 0. Our admissible space is pretty much the standard one for such variational problems, W1, 2. I don't think there's anything non-standard about this admissible space. Now for every A less than 0, there does exist a minimizer of this Landau-Dijon energy functional in our admissible class. This is almost immediate from the direct methods in the calculus of variations. And I guess our main result is that there exists some critical temperature AC less than 0, such that for all A less than this AC, the global minimizer Q cannot be purely uniaxial. So it cannot be written in that simple compact form there. So the statement is that biaxiality is inevitable for this particular model problem for low temperatures. And in the last part of the talk, I'll show you how you can generalize this to more general geometries. But for this particular model problem for low temperatures, biaxiality is inevitable. Now for the proof. Now our strategy is fairly simple to understand. The main steps, they're easy to state, maybe harder to implement. Now in the first step, we carried out a constrained minimization problem. So we looked at the Landau-Dijon energy functional, and we minimized it in the restricted class of purely uniaxial Q tensors. So not the class of all Q tensors, not the class of all uniaxial and biaxial, but a restricted class of uniaxial Q tensors. So it's a constrained minimization problem. You can prove that this constrained minimization problem is well posed. So for every A negative, you can find a minimizer, a minimizer in this constrained class. Let's call it QEA, and this it exists. It follows from the direct methods in the calculus of variation. So the constrained minimization problem has a solution for every A less than 0, and you can also prove that your constrained minimizer in this restricted class is again a classical analytic solution of this simpler set of elliptic PDEs at the bottom. So it exists, and it's a classical solution of this simplest set of elliptic PDEs at the bottom. Now the next point is regarding the boundary conditions. So we have radial boundary conditions. This is what I would call a topologically non-trivial boundary condition. Topologically non-trivial in the sense the radial unit vector has non-zero degree when restricted to the boundary of a sphere. But the constraint minimizer Q is uniaxial by definition, so you can always write it down in that form there. But the n that you see there, which is the leading eigenvector, it has to be an extension of the radial unit vector. But the radial unit vector is topologically non-trivial. So any extension of the radial unit vector must have interior singularities. But the constraint minimizer Q is analytic again. So therefore Q has to be 0 whenever n has a singularity or a defect. So the only thing that I'm really saying here is that for every a less than 0, this constraint minimizer Q must have a non-empty isotropic set. It must have a non-empty isotropic set which will contain the defect set of this leading eigenvector n. But to proceed any further with the analysis, I need 2 extra bits of information. I need some information on the location of the defect set, and I need some information on the structure of the defect set in the low temperature limit. So the low temperature limit is an asymptotic limit, but I will get some information in the low temperature limit. Now for the first question, which is the location of the 0 set, is I can prove, I can prove that if I take a sequence of these constrained minimizers, then these minimizers converge strongly in W12 to an explicit limiting harmonic map Q0 that you see there on the slide in the low temperature limit. Now if you look at this explicit limiting harmonic map, I won't give you too much of a justification, but it's actually a minimizer of the one constant Ose-Frank energy. But that's not really crucial for the rest of the talk, but there is a connection between the one constant Ose-Frank and the Landau-Duchenne here. But if you look at the formula for Q0 here, it's obviously perfectly uniaxial. It's perfectly radial because the leading eigenvector is just the radial unit vector. It has constant order parameter S plus, and very importantly, it has an isolated defect at the droplet center at the origin. Now the practical consequence of this strong convergence result is that these constrained uniaxial minimizers, they will look more and more like this limiting harmonic map everywhere away from the droplet center. So the isotropic set or the defect set of this constrained minimizer Q, it has to be localized near the droplet center, near the origin for sufficiently low temperatures. So this is giving us information about the location of the defect set. So now that I have some information on the location of the defect set, my next step is to somehow zoom into the defect core, is to sort of blow up the defect core, mathematically zoom into the defect core. And for this, I'm going to introduce some scalings. I'm not really going to explain that. I don't really want to explain the technical details, but the idea is that these scalings, they magnify the defect core as you move to the low temperature limit. And some of you will recognize that I'm actually rescaling the length in terms of the nematic correlation length. So this is really a way of measuring defect size in units of the nematic correlation length. That's really that's the whole point of these scalings. That is all that they are doing. And my next big step is to use this division trick, which has been very successful in the Ginzburg-Landau theory for superconductors. And this division trick, loosely speaking, I'm going to define a new tensor S, which is going to be the ratio of my constrained minimizer. So I'm still looking at the constrained minimization problem, which is going to be the ratio of my constrained minimizer QA divided by this function h that I've just introduced from nowhere. Now this function h is a solution of this boundary value problem here, and I haven't given you any justification of where this function came from. For the time being, just take this to be a definition, but it does come, there is a physical motivation behind it. But this function h is a solution of an explicit 2-point boundary value problem. This function h only depends on the radial distance from the origin. There are 2 boundary conditions, and we can prove that this boundary value problem has a unique monotonically increasing solution. So there is a unique monotonically increasing function h from 0 to 1. So this function exists, and therefore this ratio S is well defined. And the central result is that we can prove that these tensors S, these division tensors if you like, they converge uniformly to this perfectly radial tensor here at the bottom in the low temperature limit. If you look at the formula at the bottom, you will see that it is perfectly radially symmetric, because it's perfectly uniaxial, as you would expect, and it's radially symmetric because the leading eigenvector is again just x over mod x. So what this result is really telling you is that this sequence of division tensors, if you like, they converge to this perfectly radial tensor in the low temperature limit. So it's an exact radial asymptotic symmetry result. And here I have some more ingredients of the proof. These were steps in the proof, because we had to look at a number of different steps. We had to look at the system of PDEs satisfied by S. We had to prove that S is independent of R. It only depends on the angles theta and phi. It doesn't depend on the radial tensor. And at the end, it's actually just the radial tensor in the low temperature limit. So there were lots of intermediate, fairly non-trivial mathematical steps. So what have we actually achieved? We looked at a constrained minimization problem. So we're minimizing the Landau-Dijon energy in the restricted class of uniaxial tensors. These constrained minimizers exist, that's good. And these constrained minimizers, they converge uniformly, well, modulo a rotation, but they converge uniformly to this tensor H that I've called here, that I've labeled here, in the low temperature limit. So we just need to now think about what this tensor H represents. It's a convergence result, and what does this tensor H represent? Well, it's perfectly uniaxial, but that's to be expected because we're only dealing with uniaxial things. It's perfectly radially symmetric in the sense that the leading eigenvector is just the radial unit vector x over mod x. So everything's pointing radially outwards away from the droplet center. It vanishes at the origin, because if you recall from the definition of H vanishes at the origin. So it has an isolated isotropic point at the origin. So it is effectively describing a radially symmetric structure with an isolated isotropic point at the droplet center. But if you go back a couple of slides, this is precisely the radial Hedgehog solution. So what this has effectively done is we have somehow obtained a complete characterization of uniaxial, so equilibria in the restricted class of uniaxial tensors on spherical droplets with radial boundary conditions in the low temperature limit. So we have obtained a complete characterization in terms of the radial Hedgehog solution in the low temperature limit. So this excludes the possibility of any other competing uniaxial equilibria in the low temperature limit. So uniaxial equilibria, if they exist, well, they do exist in the restricted class, but they look more and more like the radial Hedgehog solution as we move to lower temperatures. So it's good. So you can restrict yourself to the radial Hedgehog solution if you're only really concerned with uniaxiality. But then the question is, what does this really tell us about the bigger picture? Because the radial Hedgehog solution is, well, like we've just seen, is somehow the unique uniaxial minimizer. So it is pretty much stable to all uniaxial perturbations for sufficiently low temperatures. But we can also prove, so this is again a proof, that the radial Hedgehog solution is unstable with respect to biaxial perturbations or higher dimensional perturbations for sufficiently low temperatures. You just look at the second variation of the Landau-Dijon energy, so this is again a proof. So it is stable with respect to uniaxial perturbations, but it is unstable with respect to biaxial or higher dimensional perturbations. So the conclusion then is that the global Landau-Dijon energy minimizer, so this is global in the sense with respect to all uniaxial and biaxial, in the class of all uniaxial and biaxial Q tensors, the global Landau-Dijon energy minimizer for this special model problem, I'm still restricting myself to this special model problem, it has to be biaxial for low temperatures, because if it were uniaxial, then it would be like the radial Hedgehog solution. There are convergence, it's a convergence result. But if it is like the radial Hedgehog solution, then it is unstable with respect to biaxial perturbations. So the global minimizer will have to be biaxial near the origin or near the droplet center for this particular model problem for sufficiently low temperatures. But this is a pretty specific result, because at the end of the day I'm only looking at a very special geometry. It's a nice spherical droplet with radial boundary conditions, and what we've achieved is some sort of a complete characterization of minimizers in the restricted class of uniaxial tensors in terms of the radial Hedgehog solution in the low temperature limit, and then we have used the instability of the radial Hedgehog solution to deduce that global minimizers must be biaxial for low temperatures. But we really want more general results than this, and recently we have made progress on these lines. So this is a paper that has been submitted to physical review letters. So we have to some extent generalized these results to any arbitrary simply connected three-dimensional geometry with physically realistic Dirichlet boundary data. And I obviously need to be careful about what I mean by physically realistic, but let's just say that I take the boundary to be in thermal equilibrium. So I start off with any arbitrary three-dimensional simply connected geometry with physically realistic Dirichlet boundary data, and again I am working with low temperatures. I follow exactly the same strategy as before, as I did for the simple model problem. We minimize the Landau-Dijon energy in the restricted class of uniaxial Q tensors. You can again prove that this minimization problem is well posed, so you have a minimizer in the restricted class. You have topologically non-trivial Dirichlet data, so your constrained uniaxial minimizer will have an isotropic set. You can again repeat the same protocol, the same jargon to have strong convergence to a limiting harmonic map, which I have here. But because we have non-trivial boundary data, this ND will again have a discrete set of isolated interior singularities. So this leading eigenvector ND will have a singular set, and you can again prove that your isotropic set or the defect set of your of your constrained uniaxial tensor will be localized near the defects of this limiting harmonic map, which I've labeled by Q star here. And then the trick is, once you have the localization of your defect set, is effectively to look at each defect separately and repeat the same procedure. You blow up each defect, and when you blow up each defect, you can again define a rescaled map. So again we are restricting ourselves to this constrained minimization problem. We know where the defects are in terms of some abstract limiting harmonic map. We look at each defect separately. We define a rescaled map, which is exactly what we did for the model problem, and then we use the same division trick to prove that the constrained minimizer locally near each defect will be precisely the radial, modulo a rotation obviously, will be the radial Hedgehog solution. And then you use the same argument again, use the instability of the radial Hedgehog, the local instability of the radial Hedgehog solution with respect to biaxial perturbations to prove that the minimizers, even for the more general case for this more general problem, they have to be biaxial near defect cores for sufficiently low temperatures. So I guess what was nice about this work is that all the results we had for the special case of a spherical droplet, they in some sense carried over to the case of more general geometries. Because when we rescaled near each defect individually, we recovered the radial Hedgehog solution for the minimizer in the restricted class of uniaxial Q tensors. And once we recovered the radial Hedgehog solution, you can prove that it is unstable with respect to localized biaxial perturbations. We use the instability to prove that the global energy minimizer, it has to be invariably biaxial near these defect cores for sufficiently low temperatures. Yes, and this brings me to the end of my talk, so thank you.
Thank you for a very interesting